Hi, so welcome to Math 355, Lecture 2. This is going to be the theory lecture. So in the previous section, what we did is we covered some calculations. We tried to actually figure out how would you find the inverse of something of the form, a plus b root 2 plus c root 3 plus d square root of 6. And so, strongly urge you to just go through and see how we would try to do calculations like that. All right, what I want to do today is try to finish the theory of much of chapter 5 on fields. And so we're going to start off by saying, L is an extension of fields. And we're going to choose some numbers alpha 1, alpha 2, and so on in L. And we're going to look at what happens if we take these elements and we add them to the base field K. Well, we saw before, or at least saw evidence towards it, that it's not enough to just add, say, the square root of 2 and the square root of 3. Because in the field, we have to be able to multiply elements, we have to be able to get the square root of 6. And it was highly non-trivial to show whether or not you can get square root of 6 as a combination of 1, square root of 2, square root of 3. And we talked a little bit more about that in the first section today. Is there anything else we need to add? Or is it enough to just have 1, square root of 2, square root of 3, square root of 6? We have to look at all their linear combinations. Do we get anything else? Well, what's nice is if you multiply any of these numbers by another number of this form, you're going to get a number of that form. So you might think that I don't need anything else. But what if I give you something more involved? So what if I give you things in general? I have to be closed under all multiplications, under all additions, basically under all linear combinations. And so the goal is to try to figure out what kind of fields can we get when we start adding certain elements. And sometimes when you add certain elements, depending on what the other elements are, you might not get anything. So what's truly remarkable is, if you look at the reals, we can add to the reals the square root of -1. And that's solving the equation x squared plus 1 equals 0. So the two roots to that are x equals I and minus I. And so we can let C equal R, where we're going to basically add the square root of -1. It turns out once we add the root to x squared plus 1 equals 0, we can solve any polynomial with complex coefficients. We don't have to add something else for, 2 plus, pi I, x cubed plus, square root of 3x minus 11 plus 8i equals 0. We don't have to add something new. Once we've added I, we have everything. So it can be a little bit challenging at times to see just exactly what do we get as we start to add elements. So the first result is that we have some field L over F. We choose some elements alpha 1 through alpha n. Then there is a unique field K with the following 3 properties. It lives between F and L. Is it possible that it could be F? Yeah, give me a situation where it would be F. Now, think about it in terms of the alphas you're choosing. Give me a choice of alphas where if I add these to K, where if I add these to F, it's not going to make it bigger. Yeah, if they're already in F, right? If they're already in F, by adding them, I don't change anything. So it's clearly possible that K could equal F. Alpha 1 through alpha n are in K. Well, okay, if I'm looking for a unique field K and I'm giving you numbers alpha 1 through alpha n, probably I want alpha 1 through alpha n to be in K. Then the last one is that if K prime is any other field that lives between F and L and includes alpha 1 through alpha n, then K is contained in K prime. That in some sense, there's a minimal or smallest field extension that has all the alphas. And so they denote the field as F parentheses alpha 1 through alpha n. And so this is called the extension field. It's the smallest subfield that contains both F and all the alphas. Okay, so the proof is not too bad. So look at all subfields of L containing K alpha 1 through alpha n. Does there have to be at least one subfield of L containing K and the alphas? L, right? So this is non-empty as L works. Okay, so there's at least something that works. There may be something smaller than all of L, but clearly L is going to work. Okay, so now let's try K is equal to the intersection of all subfields of L containing K alpha 1 alpha n. So you take any subfield that works and we take all their intersection. What must be true about that? What would we hope is true about this? Oh, sorry. Containing, it's not K, it's F. Sorry. These should be F's, not K. Sorry, my apologies. The intersection of all the subfields of L containing F and the alphas. So what do we know about K? Can you tell me anything about K? Good. So clearly, F is contained in K. And what else is contained in K? Oh, yeah, and all the alphas. And the reason is because each subfield of L contains F and all the alphas, the intersection contains F and all the alphas. So what do we need to show now? What do we need to show about K? So I can define K as a set. As a set, it's this intersection. We want it to be a field. So we must show it is a field. So how would you show something as a field? Okay, say it again.
Well, all elements have inverses.
All non-zero elements have inverses, right? We basically have to show that all the field properties hold, right? So we have to show it's a ring, we have to show that there's inverses. And so this might remind you of some issues from linear algebra. You know, every now and then it's actually nice to use a class that's a prerequisite, right? How do we show something is a vector subspace? Well, a vector subspace is just a vector space that lives inside another vector space. And so we had this really simple test. If I take two elements, you know, V and W, and I take any two numbers A and B, then the linear combination AV plus BW has to be in what I believe is my subspace. And if that works for all V and W and all A and B, then it is a subspace. So we have to go through and we have to show that all the conditions hold. So must check all conditions. Most and we haven't used this word in a while. Why should most of these conditions be true? Inherited, right? We haven't talked about inheritance in a while. But most of them are going to be inherited. So we just have to roll up our sleeves and go through and check and see. You know, associativity, is that going to be true for the intersection? Of course. You know, they all live in fields where they're associative. And so the difficulty, what do you think is going to be the hardest one? Or the hard ones? So what do you think is going to be the hard properties to show? I'm sorry? Inverses, and there's something else which people often forget. Closure, right? You have to check and see, is it closed? You know, if I give you the number 5, 5 has an inverse. It's just the inverse is not necessarily in the space. So we have to show it's closed. So given x and y in K is x plus y and x times y in K. Well, if they're in the intersection, so as x and y are in K, they are in every subfield of L containing F, alpha 1, and alpha n. By definition, right? Because we said K is the intersection of all the subfields. So if x and y are in K, then they must be in everything. Well, if it's in a subfield, then x plus y is in every subfield of L containing F, alpha 1, alpha n. Why is that true? Say S is a subfield of L containing F, alpha 1, alpha n. Since x and y are in K, that implies x and y are in S, right? But S is a field, so x plus y and xy are also in S. And S was arbitrary. As S is arbitrary, we get x plus y and xy in all subfields. Thus, xy in K implies x plus y and x times y are in K. And so the rest of the analysis is pretty similar to this. Okay. Is everybody comfortable with the proof like this? The idea is we need to show all the properties hold, so we can roll up our sleeves, check every single thing. The hardest parts are the closures and the inverses. Well, what about the inverses? And x inverse is also in S if x is not 0. So we show that you give me any non-zero element, it's in every subfield because it's in the intersection. So X inverse is in the intersection. And we're done. So I'll leave it to you to go through the rest of the details for this. And then this is going to be the smallest. And it's going to be an interesting question to try to figure out what does the structure of this look like. So just add one more page. So earlier, we had the rationals. And then we could add the square root of 2. We could add the square root of 3. And this was all the things of the form a plus b root 2, where a, b are rational. And this would be all things of the form a plus b square root of 3, where a, b are rational. And then we talked about the field q square root of 2 square root of 3. And we really didn't explain this notation before, but it was a plus b root 2 plus c root 3 plus d root 6, a, b, c, d rational. And so in the last lecture, and again, this was done in section 1, this was the lecture you were supposed to have watched, we were talking about it's not enough to just look at things in the form a plus b root 2 plus c root 3. We have to have the square root of 6. And there's no way, and this is not easy to prove, there's no way to write the square root of 6 as something times 1 plus something times root 2 plus something times root 3. We needed to do some work. And so the question now is, we have 2 different ways of getting up to q root 2 root 3. I can first go to q root 2, or I could go to q root 3. And one of the big questions, and if you continue on to Galois theory, this is going to be one of the big themes, the big questions you're going to try to look at, is the structure of these different extensions. What are the degrees? How do I get from one to the other? When I start adding these different elements, joining these elements, what emerges? And so when we're looking at this, it's not immediately clear how many things we're going to need. So when I say I want to look at root 2, root 3, what's the field where I take the rationals and then my alpha 1 is root 2, my alpha 2 is root 3. And we didn't prove it in section 1, but we said it should be of the form a plus b root 2 plus c root 3 plus d root 6. We know we need a square root of 6. The question is, can we get the square root of 6 through root 2s and root 3s, or does the square root of 6 come in a completely independent way? Do we need that as something separate? What about, instead of using things like square root of 2, square root of 3, what if I used things like the square root of 5 plus the square root of 7? There's something more involved. Maybe the square root of the quantity, square root of 2 plus square root of 3. So I've got a square root nested inside a square root. How do I start handling stuff like this? What is it going to look like? These are really interesting, challenging questions in trying to figure out what is the minimal field that's going to have both root 2 and root 3. Now, if you look at this, can you give me a basis for these? What would be a basis for root 3, for q root 3? So I want to write everything as a linear combination of the basis elements. Any thoughts about what could be a good basis for q root 3? 1 and root 3. And similarly, a basis for square root of 2, q root 2 would be 1 and root 2. And then over here, what do you think a good basis would be for q root 2 root 3? What would you guess? 1 root 3. So just these 3 elements? So anything can be written as a linear combination of those 3 elements. If that was the case, I wouldn't have the d root 6 term.
We cannot multiply.
We can't multiply. It's a linear combination. So I'm trying to write it, I'm trying to view these as vector spaces. and then a root 6. Now, unfortunately, everything is really small in terms of the degree, but this is basically a degree 2 extension. And over here, this is a degree 2 extension. And if I go from here to here, it's a degree 4 extension. So how do you think things work as I move up? So if I have a field F over here, and then I have a field K and a field L, and maybe this is degree D2, this is degree D1, what should this whole thing be? What do you think? I'm sorry? So one possibility is you add them. Or you multiply them, right? This is the problem of looking at a degree 2 extension with a degree 2 extension. 2 times 2 is 2 plus 2. So when you're looking at small cases and trying to build intuition, which I strongly encourage you to do, in this case, it's not clear, am I adding the degrees or am I multiplying the degrees? So let's say I gave you 1 square root of 2, square root of 3, square root of 5. What numbers do you think you would need? So you have to now consider all multiplications, all additions. We know we would have to have, a plus b root 5, I'm sorry, plus b root 2, plus c root 3, plus d root 5. What else would we have to have? Plus root 6, plus e root, so let's try to do it in order, root 6. What do you think the next one would be? Plus root 10, plus f root 10. What's next? Plus g root 15. Anything else? H root 30. So this is 8. So this looks like an 8-dimensional space. And so if I start off here with Q, and then go up to Q, root 2, root 3, and then Q, root 2, root 3, root 5. This is degree 4, and this whole thing here is degree 8. What do you think it's going to be if I take Q root 2, root 3, if I take that field and I add root 5? Does that feel like that should be degree 2? So looking at this, and again, I'm not doing everything fully rigorously, I'm just trying to build intuition. How do you think the degrees work? What would you guess for the degrees? Yeah, so this is suggesting we multiply degrees. And again, before I go and try to prove theorems, it's nice to get some intuition as to what do I expect. Instead of looking at the square root of 2, what might be an interesting thing to look at? These are all giving me degree 2 extensions. What might be interesting? Yeah, what if I tried to take a cube root? And then try to explore like that and build some intuition. Okay, so let K over F be an extension of fields. We've been talking about this, let's just make it a little bit formal. The degree of K over F, denoted by bracket K colon F, is the dimension of K when viewed as an F vector space. So this means I want to write everything in K as a linear combination of things in F. And I need to choose a basis. So a basis is a set of vectors that are spanning and they are minimal. I can't do it with anything smaller in size. So there are infinitely many bases for R2. Normally we like to use the X and the Y axis directions, but I could use anything I want as long as they're two different directions. If I give you three vectors in the plane, say the X axis, the Y axis, and the 45-degree line, do those three vectors span the plane? Yeah, they span the plane, but they're not linearly independent. I don't actually need all three of them. I can remove any one of them and still be okay. So again, we're trying to go back now to linear algebra. So the degree of K over F is basically, how many elements do I need to span? And what we were saying was we were looking at Q root 2. So Q root 2, the degree of that over Q is just 2. And it's looking like Q root 2 root 3 over Q was equal to 4. And Q root 2 root 3 root 5 over Q was 8. And then trying to figure out what are the basis elements. And so here it would be 1 root 2. Here it would be 1 root 2 root 3 root 6. Here it was the 1 root 2 root 3 root 6 root 10 root 15 root 30 if I didn't miss anything. I think I did miss something. Oh, sorry, it's I missed the root 5. Root 5, root 6. Okay, so does this notation look like anything you've seen before? It's been a while, but we have seen something like this early in the semester. So if you go back to groups, when we were looking at the cosets, right, how many cosets do we need to get up to the full group? How many translations? All right, so the first is the result that I've been hinting at, the multiplicativity of degree in towers of fields. So L is an extension of K is an extension of F. And so if both of the degrees are finite, so if the extension of L over K is finite and K over F is finite, then L is finite over F. That kind of makes sense. And they satisfy the relationship that the degree of L over F is the degree of L over K times the degree of K over F. And then if one of the degrees is infinite, then the other one is also infinite. That's part B. So what I want to do is I want to sketch the proof of A. Okay, so we want to do A. Let's try to think about what does it mean. So if K is an extension of F, let's say the degree of K over F is M. Let's say the degree of L over K is N. So here is my F all the way downstairs. Here's my K. Here's my L. It's going to be M to get to here, N to get to here. And we want to show that this is M times N. Oops. Okay. So what does it mean for the degree of K over F is M? So any K in K of the form, let's do it as alpha 1 F1 plus dot 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 plus alpha M Fm. And here, any L in L of the form beta 1 K1 plus dot 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 plus beta n kn. So here, F1, Fm is a basis for k over f, and then k1 to kn is a basis for L over K. Slightly different notation in the book, just so I can look down and just see where things live very easily. Okay, so I'm basically saying I can write anything in F as a combination of some basis elements. Let's call the basis elements F1 through Fm. Where do the coefficients alpha live? So where do the alphas live? So we're trying to write anything in K as a combination of things in F. So where are the coefficients? Where do they live? Where do they come from? They come from F. So here, the alphas are in F. Where are the betas? So where do the betas live? Okay. Now maybe this notation is actually bad and maybe it's confusing. Where do the F's live? So I really, maybe I should not be using them as F's. I apologize. I'll get rid of the K's. So if I'm taking the basis elements, where should the basis elements live? They should live, the first one should live in K. So it should be really, K, oops. So it should really be K1 through Km. If the K's lived in F and the coefficients live in F, where would that linear combination live? It'd have to live in F. So if I want to write, K as an extension of F, my basis elements clearly can't live in F because then their combinations are only going to be things in F. I'm adding some things. Those things that I'm adding, those are things in K. Think of it as your square root of 2 and square root of 3. I don't need that many of them to form a basis. I just need a few of them. And then similarly, when I'm looking at L over K, where should the basis elements of those live? They should live in L. So I'll call it maybe L1 through Ln, and those should live in L. So now I need to come up with basis elements for L over F. Thoughts for basis elements of L over F? We need m times n objects. We believe the degree should be multiplicative. So again, the reason I wanted to do some of the other problems first is to try to give us some intuition as to what the answer should be. We're looking for m times n elements to serve as our basis. Any thoughts about what we should try? So we have the basis elements K1 through Km, which is a basis for K over F. We have L1 through Ln, which is a basis for L over K. I now need m times n objects that I think might be a basis for L over F. What could I try? There aren't that many ways to get m times n objects. Yeah, so try K1, L1, K1 L2 dot 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 all the way down to Km Ln. That gives me m times n objects. I can take anything in L and I can write it as something in K. And I can take anything in K and write it as something in F. So this should give me a way of writing anything in L as something in F. So, given, X in L, we can write X as, maybe X1, L1 plus dot 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 plus Xn, Ln, where each Xi is in where. The L's are a basis for L over what field? Nope, they're not a basis over F. Well, where the L's the basis of? The L's are the basis of L over K. I'm sorry? So we have a basis of L over K. So that means I can write anything in L as a combination of these basis elements where the coefficients are in K. So you give me an X, I can write it as a combination of the basis elements. Where do the X's come from? They come from K, right? This is the definition. We're saying we have a basis for L over K. So that anything in L can be written as a combination of L1 through Ln, our basis vectors, and coefficients. And where do those coefficients live? They live in K. So if I give you some X in L, I can write it in terms of the basis, and my elements, X1 through Xn, have to live in K. But we have a basis for K over F. So each Xi, I can write it as maybe Xi1 K1 plus dot 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 plus Xim Km. Where do all the Xij live? Those should be an F, because we have a basis for K over F. That means you give me anything in K, I can write it as a combination of my basis elements where my coefficients are in F. So if we expand, we get, X is equal to X11 K1 plus dot 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 plus X1M Km L1 plus dot dot dot. And so when you expand it, you'll get, like X11 K1 L1 plus dot dot dot. And this is going to be an F. So does everyone see I'm doing it as a two-step process? I first take something in L, and I can write it as a combination of my basis vectors in L, and the coefficients are in K. Now I take those objects in K, and because I have a basis for K over F, I can expand those out, and I have those coefficients in F. And so when I just substitute, I have now written every X as a combination of K1, L1 through KMLN with coefficients in F. So this shows that the set is spanning. So it shows K1, L1, dot, 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 KMLN spans. Is that enough to prove that it's a basis? What's the issue? We have to show they're linearly independent. So before we move to linear independent, I want to make sure everybody understands this because this is the key part. And if you're having trouble here, the people who are watching this at home are probably going to have trouble as well. So if anything is not clear, speak up. It's a two-step process. We first write anything in L in terms of its basis, and the coefficients are going to be in K. Well, we have a basis for K in terms of F, so we can expand those out. So is everybody okay with the two-step process? All right, so now we just have to show linearly independent, okay? Must show K1, L1, dot, 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 K, was it M, Ln, are linearly independent. Okay? So let's assume that we have some sum of C, Ij, Ki, Lj equals 0. So I goes from 0 to M, J goes from 0 to N. So what do we need to show to prove that they're linearly independent? So what must we do to show that they're linearly independent? So if I give you a bunch of vectors, and I tell you a linear combination of these vectors sums to 0, and I want to show that they're independent, what's the only way a linear combination of independent vectors can sum to 0? The coefficients are all 0, right? If I give you the x-axis, the y-axis, and the 45-degree line, I can take the x-axis plus the y-axis minus the 45-degree line, and that's going to sum to 0. Those three vectors are linearly dependent in the plane. I need to show, so must show all the C's vanish. Okay? Well, we can do this in stages. So this is the same as the sum, I goes from 0 to M of C I1 Ki times L1 plus the sum I goes from 0 to M of Ci2 K2. I'm sorry, Ki L2 plus dot 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 plus the sum I goes from 0 to M of C I N Ki times Lm. I'm just taking all the things that hit L1, all the things that hit L2, all the things that hit L3. Everybody comfortable with this? But what do we know about the L's? The L's are linearly independent. So because the L's are linearly independent and this sum vanishes, so as L1, L2, dot, 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 L, oh, this should be Ln, I think. That one should be Ln. Ln linearly independent, only way a linear combination can be 0 is if each coefficient is 0. Right? So now we know C, I'll leave it as a sum, I guess. The sum I goes from 0 to M of Ci1 Ki equals 0, dot, dot, dot. The sum I goes from 0 to M of Ci n ki equals 0. But what do we know about the k's? They're also linearly independent. So for example, this one over here is just the same as C11K1 plus C21K2 plus dot 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 plus CM1KM equals 0. As the k's are linearly independent, that implies these c's are 0. And so we can just march down, and each one of these, they're all going to have to just be summing to 0. So again, it's another two-step process. We look at the linear combination, summing over all the i's and j's. Well, let's collect everything in front of L1. Let's collect everything in front of L2. Because the L's are linearly independent, the only way the sum can be 0 is if the coefficient of L1 is 0 and the coefficient of L2 is 0. All right, well, now that we know that the coefficient of L1 is 0, if we look at that, it's a linear combination of the k's. And the k's are linearly independent. So the only way that can be 0 is if all those coefficients are 0. So when the dust settles, every coefficient is 0. And that finishes the proof. Okay, so this shows us that our guess that it was multiplicative worked, and our guess for a basis worked. This is the method of divine inspiration. I can write everything in L in terms of K. I can write everything in terms of K in terms of F. I should then be able to link these two and write things in L in terms of F. Okay. So looking at this, this is now a higher level way of seeing that if we take root 2 and root 3, I probably need something else for my basis element. Whether or not root 6 works is another story. Okay. So the next is polynomial rings. So let F be a field, little f of f with square brackets x, the square is very important here as opposed to parentheses, means that we have a polynomial of finite degree with coefficients coming from f. So these are polynomials of finite degrees, a0 plus a1x plus dot dot dot, where all the a's live in f. So here, each ak is in f. And when we write it out, because it has a finite degree, we will assume that AD does not equal 0 when we're writing it out like this. If we want to then say that D is the degree of F. Okay, so if I give you a cubic, what should be the degree of a cubic? 3. Now, if I give you 0x cubed plus 3x squared, well, I could view that if I wanted to as a cubic with just 0 leading term. I really don't want to do that. I really want to call that a quadratic. So frequently, we want the leading term to be non-zero. Now, it says by convention, we set the degree of 0, the 0 polynomial, to be negative infinity. It's been a while since we've actually had an infinity involved in our math classes. What should the degree of f times g be? What's our hope? The degree of the polynomial f of x times the degree of the g of x. What should that be? I guess typically we don't write the x's, we'll just write, fg. What should the degree of a product be? Yeah, we would expect it to be the degree of f times the degree of g. If I give you something of degree 4 times something of degree 5, it should be degree 20. I'm sorry? Well, let's try it. The degree of x to the 4th, x to the 5th.
Oh, wait. Oh, no.
Yep, I think you're about to fix it.
Yeah, it's a plus.
Yeah, it should be a plus. So we want a plus sign here, not a product. And so this would be 9, this would be 4, this would be 5. So this suggests that we want a plus sign. We haven't proven this yet, but it seems reasonable that the degree of a product should be the sum of the degrees. Okay. Does this motivate now why the degree of 0 should be negative infinity? So if I give you the degree of the 0 function times f, that should be the degree of 0 plus the degree of f. Well, this is the same as the degree of 0. So if the degree of f is not 0, the only way this can work, so we need the degree of the 0 polynomial to be negative infinity for this to work. Okay. Just go back. Now, when we look at this, we're assuming f is a field, right? What if f was not a field? Can somebody give me a ring which is not a field? Good, and what's our favorite clock? 12. So let's consider z mod 12z. Can somebody give me a good choice for f? I'm sorry? Yeah, let's make it a little bit meaty. Say 3x to the 5th plus 1. And what should we take for g of x? Not 2.
Oh, no, 4.
4. Let's take g of x to be 4x. Then f of x, g of x is 12x to the 6th plus 4x, which is really the same as just 4x. So degree of fg is not the degree of f plus the degree of g. So the problem is we have divisors of 0. Notice that I am not claiming at this point that we've proven that the degree of a product is the sum of the degrees if we have a field. I'm just saying if we don't have a field, we clearly cannot have this happen. So you always want to get a sense of how important are the different words. Does f have to be a field? Yes. If f has 0 divisors, things can break down. And that kind of makes sense when you're looking at the polynomials hitting each other. If their coefficients align properly and their divisors of 0, then you can lose that highest degree. And then the argument is just that as long as you avoid that, you're fine. And so I'll leave this as an exercise. But if f of x is of the form, say, a m x to the m plus ... and g of x is of the form, a n x to the n plus ... then f of x, g of x is going to be of the form a m x to the m plus n plus ... and a m n. Oh, sorry, I can't use a both times. Sorry. I will use. I'm sorry? Yep. It's basically not 0. Right? And the only thing that you have to be careful about is how do you want to deal with the 0 polynomial? And so the way to make this work is negative infinity. Can you add negative infinity to a finite number? Yes. You have $1 million in the bank. You owe me negative infinity dollars. How many assets do you have overall? Negative infinite. If I replace your billion with a trillion, it doesn't matter. You're still beyond broke. What if I say you have infinitely many dollars in the bank and you owe me infinitely many dollars? Can we handle that? Can we deal with infinity minus infinity? No. So these are the things you have to avoid. You cannot do infinity minus infinity. What else can't you do? It's not a real number, but informally, 5 minus infinity is negative infinity. I'm fine with that. 5 plus infinity is infinity. I'm fine with that. Yeah, 0 times infinity. We can't do 0 times infinity. Right? What else can't we do? We can't divide by infinity. Well, can we?
We can, but
There's one thing we can't divide by infinity. Infinity divided by infinity, that I can't do. And as long as we're doing things to avoid, there's another division we should avoid. Yeah, definitely dividing 0. Now, if I have infinity and divide by 0, then that should probably be a huge infinity. Maybe I don't know the sign, but it's huge. But what should I be careful about dividing by 0? Yeah, 0 over 0 is definitely bad. Maybe anything over 0 is bad, but well, 5 divided by 0, I can view that as maybe infinity. But these are the ones we have to avoid. But what's okay is, a fixed real number minus infinity, a fixed real number plus infinity, a fixed real number times infinity, a fixed real number divided by infinity. These we can actually make sense of. Okay, so the next is division with remainder for polynomials. So if I give you a field, and I give you 2 polynomials f and g in the field, f joint x. So these are polynomials of finite degree. Let's assume g of x is not equal to 0. Then I can write f uniquely as some multiple of g plus a remainder where the degree of r is less than the degree of g. We've basically been doing this for real numbers. Oh, I'm sorry, for integers. This was your division with remainder. And we had some way of measuring, some way of comparing 2 different numbers. When we did the Euclidean algorithm and we were doing divisions with remainder, the remainder was always smaller than the number. And because it was smaller, the process had to terminate in a finite amount of time. Because you can't have an infinite chain of positive or an infinite chain of non-negative numbers. Eventually you're going to hit 0. So here we have something similar. We have the degree is smaller. And so eventually we're either going to get all the way down to degree 3, degree 2, degree 1, degree 0, and then after 0 comes degree negative infinity. There's no degree negative 5, there's no degree negative 6. We go from degree 0 to degree negative infinity. And so the idea is proof by induction. So the proof is in the book. It's a good idea to try to do it yourself. If I give you, say, f of x is an x to the n plus ... and let's say g of x is b m x to the m plus ... and let's assume maybe n is greater than or equal to m. If m is less than if n is less than m, then that means the degree of f is less than the degree of g. We've already got our remainder. We're done. So now what we can do is we can look at f of x minus what multiple of g would you want to subtract to get rid of the highest degree? So f of x starts with an x to the n, g of x starts off with bm x to the m. What would we want to multiply g by? Let's do it in stages. We want to get the right power. So this is a n x to the m. This is bm x to the m. I want to get up to the power n. What should I multiply g of x by? What power of x? Sorry? X to the n minus m. And then what coefficient do I want to put in? I want to cancel out the leading term, which is an x to the n. Yeah. And then this is going to equal, let's call it, c n minus 1, x to the n minus 1, and then we're done by induction. Because we were able to get something of smaller degree. And of course, note bm does not equal 0 as the degree of g equals m. And here, it's very important that we have the ability to take B inverse. This is where we use a field. If F isn't a field, may not have B inverse, BM inverse. So really, I should probably write this really as maybe AN BM inverse. But just, since we're assuming things are commutative and whatnot, use of notation, let me just write it like that. And so what we did is we took our function f, we subtracted a multiple of g so that what we're left over with has a smaller degree. Yeah, everything okay?
Yeah.
And then just allow the rinse repeat, then just keep going, keep going, keep going. And so if you want to, you could say, let's proceed by induction, assume we've done it for all f of degree at most n, let's do it for functions of degree n plus 1, and then you would subtract off like this, and now you would have something of degree n, and you're done. And the inductive case, the base case, well, if the degree of f is small, it's trivial. What's the remaining thing that I have to show that I haven't shown yet? So we showed we have a decomposition. What else do we have to show? Uniqueness. So I'll leave it to you to show uniqueness. And again, after break, if you want me to do uniqueness, I want to alternate theory and lecture, I'm happy to go through and do more details and go through and do uniqueness. But there's too many theorems to do every step for every theorem. So you should be able to do uniqueness. It's a good exercise to try to do it. Hopefully you can just look at it and see, okay, if I had two different things that worked and I would subtract them, what would happen if they had different remainders? And just play games like that. Okay, so the next is if F is a field and I is any ring that is contained in F adjoint X, the polynomials of finite degree with coefficients in F, then I is a principal ideal. And this is similar to what we saw before when we were looking at the integers, that any of the ideals they would generate because we took something of the smallest positive integer, and if we had something that wasn't a multiple, then we could look at this decomposition. And so proof that principle. So let G be a polynomial of smallest degree in I. Without loss of generality, let's assume I is not the zero ideal. We understand the structure of the zero ideal. That's principle. And just so we need to show that I is principal. So G is a polynomial of smallest degree. If F is in I, then I can write F of X as Q of X, G of X plus R of X, where the degree of R is less than the degree of G. But R of X equals F of X minus Q of X, G of X. Where does that live? So we have I is an ideal, F is an I, G is in I. So if we multiply something in the ideal, it's got to stay in the ideal, right? So this is in I, and the combination of two things in the ideal is in the I. So R has smaller degree. There's only one way that this can work. What must be true? So I'll make the smallest finite degree. R0. So must have R of X equals 0. So F is a multiple of G. So it is principal. So it's very similar to the argument we had before when we were looking at just integers. You know, we take something of smallest degree. I've got to be careful. I'll say smallest finite degree. There could be multiple G's that we can take. That's fine. I just choose something that has smallest finite degree. And I take anything else that's in the ideal. And then we show that, well, wait, we could actually find something with smaller degree. The only way that that's going to work is if this degree is negative infinity, which means that this is 0. Okay. So the next is building extension fields. Let's see how much we want to get to. So we're talking about reducible and irreducible polynomials. So if I give you x squared minus 1, can you factor that? Yes, and the factorization is x minus 1, x plus 1. What if I give you x squared plus 1? Can you factor that? Yeah, so this is x plus I, x minus I in the complex numbers. But no factorization over the reals. There is another way to factor x squared plus 1 in another field other than the complex numbers. So consider R is equal to z mod 2z. So what does 2 equal? 0. So x squared plus 1 is the same as x squared plus what? Yes. So what would that equal? Yeah, x plus 1 times x plus 1. So whether or not something can be factored depends on where we view it. So x squared plus 1, I can factor this over the complex. I can factor this over z mod 2z. I can't factor it over the reals. And it becomes an extremely important question to determine when can a polynomial be factored. If a polynomial can be factored, what would you like to know next? So if I tell you I can factor a polynomial, what would you like to know? How, right? What are the factors? We saw that Fermat's little theorem can be used to determine that certain numbers are composite without actually telling you the factorization. Prime factorization is difficult. Primality testing is actually not as bad. And so you can be in the amazing situation where you know something can be factored without knowing what the factors are. Does that extend? Probably because the integers are special cases, but maybe not. Maybe things are nicer in a situation like this. It's things to just be aware of as we continue in the subject. So I'm not going to go through the details of theorem 5.26 and 5.27. I just want you to be aware that results like this exist. So if you have fields and you have a polynomial, and if the polynomial is irreducible, then you can look at all these different, rings and stuff that are generated by this, and you have all these wonderful results. Okay. I want to end very quickly with the following key fact about finite fields. So if F is a finite field, so it's a field with only finitely many elements, there are three things. The characteristic of F is prime. So 2 is 0, 3 is 0, 5 is 0. Some number of copies of every element is going to be 0. And that number of copies is going to be a prime number. Then the characteristic, we'll denote that by P for prime. It's a subfield. Then the finite field FP, which is a very special field, this is just Z mod PZ, is a subfield of F in the sense that we can basically embed it somehow. And then any finite field, the number of elements is just P to a power. The last one, the reason this is true is because I can view this as an extension over FP. I can write it as some kind of combination of basis elements. So I can write something in F as maybe, A1, let's call it F1 plus ... plus, AK, FK. I have a basis with K elements, and the A's live in the finite field FP. And so the number of choices is going to be P to the K. And that's where the last one comes from. The most interesting is that the characteristic of F has to be a prime. So proof of A, I just want to quickly sketch this. We know that we can always map, the integers into various things. We have all these different ring homomorphisms and whatnot. So we want to consider a map from Z to our finite field F. What do we have to send 0 to? 0. What do we have to send 1 to? 1. And so now the question becomes, as we keep going, eventually something has to be sent back to 0. Right? There should be some smallest number that's sent to 0. So assume, phi of M equals 0 with maybe M equals AB. And let's say A and B are greater than 1. We want to somehow get a contradiction. What's true about phi of a product? I'm sorry? Is the product of the phis. But F is a field. These are in F. F is a field, so it has no divisors of 0. Right? But if this equals 0, then either phi of A equals 0 or phi of B equals 0. And this contradicts the minimality of M. So we were choosing the smallest M. If I give you phi of P, where P is a prime, I can write that as, P times 1, which is phi of P, phi of 1. Well, what does phi of 1 equal? 1. This is not a contradiction. I'm not really getting divisors of 0. I'm just getting 0 times 1. And so if the characteristic is not prime, if I can write it as A times B, then this contradicts the fact that M was supposed to be the very first time we had to go to 0. Because phi of a product is the product of the phis. I don't have divisors of 0. So one of these has to be 0. And so M is not going to be the smallest thing that works. All right. So this is a good place to stop. I am happy to do more problems on this next week, which is, of course, many weeks from now. But I wanted to at least finish going through all the material of chapter 5 first before going to spring break.